Recording here.
Okay. I have to click everybody has to click the okay.
Yep.
All right. Now,
Right. Yeah.
I
Welcome
need,
everyone.
yeah, go ahead.
Yeah, I'll do a quick this case.
That's
I know
right. Yes.
a lot of you are veterans, so we won't belabor this too much, but thanks everyone for coming. Thank Eric for presenting. Again, we're always looking for speakers, always looking for topics. So if you have any ideas or something you want to share with the group, please reach out. Happy to make that happen. Probably it didn't happen this time, but probably considering in-person events sometime in the future, but happy to keep our remote guests as well. Yeah, I think that's about it. I'll turn over to Eric and we can get the show started.
Sounds good. Thanks, Andy. Let me go ahead and share my screen here. Hope I get the right one. Here we go. I'll do the slideshow thing. All right. So today's talk is called "What's the Big Deal with Folds Anyway?" And this kind of comes out of some experiences I've had as a developer and continuing to learn new things and stuff. So I'm going to kind of talk about that a little bit. I hate kale. So everybody at Rally knew me as the guy who hated kale. So I use that image a lot. And I use the name Kaleergic around places. So if you see me, that's who I am. I currently work at Tubi. I work in growth engineering. And I've been there for a couple of years. We're hiring. So if anybody's interested in Tubi, you can find us on your nearest smart TV. We are ad-supported video on demand. So very interesting space. The Scala stuff that we do is all in the ad tech space for the most part. I mean, there might be some other stuff, but our Scala developer teams are in the ad tech space. All right, so who am I? I love programming. I've been doing this kind of work for 25 years. I have a bachelor's and master's in CS. I've worked in lots of different industries, and I was a Java guy for about 15 years. I was a Scala guy. I have been a Scala guy for like the last 7 years, and I've been trying to get myself to move beyond the old Java way of doing things and you know, do things more functionally. And so I'll talk a little bit about how I got into learning Haskell as the talk progresses. And of course, I hate kale. I said that already. So that's me. Okay, we're going to start with just a basic example of something that we all learned how to do in Programming 101. And this is a Scala version of it, but this is Scala iteration. And what we're doing is we are essentially just summing up the list of integers. So we have 10,000 integers and they're 0 to 10,000. I shuffled them here. And we have a for comprehension in Scala, and we're summing these things and we print it out and we get an answer, right? And that's pretty basic, right? And yeah, so that's how you do things in a lot of languages. But in Scala, we don't really want to iterate. And when I was learning Scala about 7, 8 years ago, actually, you know, everybody's like, "Oh, Eric, you got to try this fold thing. Folds are awesome." And I was like, okay, that's interesting. So what are folds? So what the heck is a fold? So you can get into some category theory, which I won't. I'll just use the word and then I'll talk about what it is, but I'm not going to talk about category theory. But here, this is the only where there's no monoids in this talk. There's no monads. There's no functors, applicatives, none of that. But the word catamorphism, you're deconstructing data. And according to the Haskell wiki, a fold is a higher order function that processes a recursive data structure and returns or reduces it to some value. It's also called a reduce. And I think we all know what a higher order function is. It's a function that takes functions as input and or produces functions as output, or a function as output. So that's a higher order function. And so all this is like great. It's a lot of words, a lot of description. So let's look a little bit more. Oh, and before we do that, we'll talk a little bit about like why we would use a fold. I found a great reference, and so I added the attribution at the bottom here. But these are the kinds of things you can do with a fold. You can do binary operations on some elements of a list. I say be careful with non-commutative operations, because if you use one kind of fold and you use a non-commutative operation, you might get a different result with a different kind of fold. You could do things like find the max, min, average count of elements. You can count the number of occurrences. You can uncount, you can undo that count and re-expand your list. You can find an element in a list or a bunch of elements. You could like look for all even numbers, for example. You can deduplicate, you can reverse, you can convert a list to a set. You can even do an insertion sort. I didn't look in depth at that example. You can create sublists of a specific size. And then I was sort of like, oh, this is feeling a lot like, as I was studying folds, like there's that old gang of four design pattern called chain of responsibility. And I did find a blog post where, and maybe that's another talk, but like I linked it here because like I thought it was interesting. You can actually implement the chain of responsibility design pattern as a catamorphism. So that's probably another talk, but these are some cool things you can do with folds. Okay. So let's look at some folds in Scala. And this is pretty basic, right? So instead of that little iterating thing I did before in that earlier slide, here what we're doing is we're saying, okay, I'm going to fold over this list of ints and I'm going to sum the elements. And I get the folded sum is the example, the error, or sorry, the answer that we expect, right? And that's the fold function in Scala. And this is defined as being like on, it's a member of a collection, right? One of the collection classes, right? So that's what we're looking at here. And there's this other thing called findLeft. You can do something very similar, and you get the same answer. And then there's another thing called findRight. You can do something very similar, and you get the same answer. Okay, so let's dig a little deeper. Oh, I guess this slide has a little bug on it. I guess I'll fix that later. Sorry about that. So let's dig a little deeper. This is the definition of the first one we looked at, fold. And this is on this trait called iterable once. And fold is defined in terms of foldLeft. And it's a higher order function because you can see there's a function being passed in. There's this operation, right? That's taking two operands and combining them into a result. So this findLeft thing, let's look a little deeper. Okay, well, this is a little disconcerting. Everybody's telling me that folds are so cool, and I'm learning Scala, and I stumble upon this, and I'm like, well, okay, but why? Like, what's the big deal? So I'm passing a function around. Whoop-dee, why are folds so exciting? And here, like, you know, when we look at findLeft, what we see is we have an iterator and then we're doing a while loop. Well, that's really not that much different from what we're doing in our basic iteration example. And this, I contend, is lipstick on a pig. I mean, you're not really doing much more than you were doing before. In fact, I'll demonstrate a little bit like why I think it might be a little bit worse this way, because you're basically delegating control of the loop. And if you decide you want to exit early, you can't really do that. It's very hard. So folds are glorified iteration. And then if you look at findRight, then it gets even worse. You got lipstick on a pig airbrushed. So you're trying to make it look better, but it's really not doing much. It's still, you're iterating twice. You're reversing, and then you're doing this findLeft call, which, as we saw, does that while loop. Okay, so let's take another example. Let's look at finding an element. So in this case, I have an old school iteration implementation where we have a while loop. It's kind of in the middle of the slide. The while loop there is saying, okay, well, I'm going to walk through the array, and if I haven't found the result, and notice I'm using a var here, if I haven't found the result, I'm going to keep looking. And once I've found it, I'm going to exit the loop because the second loop condition is going to fail. And so I exit the loop. So I've avoided unnecessary like iteration through elements that I don't want to iterate through because I found what I'm looking for. And so we get an answer. Now this next slide, I was challenged to try to look at this. I did not even know that this existed in Scala. Don't do this. If you do this, if you work on my team and I see code like this, I might like quit that day or something. No, I wouldn't quit, but I would probably like be like, okay, why are we doing this? So what this thing does, and it's kind of interesting because I've been doing Scala for 7 years and I hadn't even heard of this, and my friend points this out to me, and I'm like, okay, this is kale. This is gross. This is disgusting. Like we're throwing an exception, and then internally this breakable thing is catching it, and then like returning control out. Oh gosh, this is we don't do things like this in Scala, so please don't do it. So I have to just call this out because somebody suggested that I try it, and we learn something new every day. So now we're going to use findLeft. This is the Scala findLeft to find an element. So this kind of illustrates what happens when you kind of like to exit your loop, but you can't. Like, so we know this is a loop because it's an implementation of a loop. We've delegated control to the findLeft function, and this is just maddening. It's like, okay, if I find the thing, I just have to keep going. I have to go through all the elements of the list. Like, this is just grossing me out. I don't want to do this. I don't want to use this findLeft thing for this. It's just crazy. So as a Scala developer, I like to get crafty, and I do stuff like that, because now what I've done is I've said, okay, I'm going to create a tail recursive function that I can exit when I want. I can be a little more interesting and use this tail recursive annotation, which is kind of cool. And I stop when I'm done, and I don't have to, do extra cycles to do this. Now, I used to work in finance 20 years ago, and thinking about how many cycles, I guess you wouldn't be using Scala in that case, but thinking about how many cycles that you're wasting is something that I do. And so this is how I am more likely to implement something in Scala, just using basic vanilla Scala. All right, so during the, this leads me to what I said earlier, during the pandemic, when the pandemic started, I got together with a bunch of friends on Zoom, and we decided that we wanted to challenge ourselves to become better Scala programmers. And many of us have had the experience, you go to conferences and you hear people talk about Haskell sometimes, and you're sort of like, oh, that's interesting, but I don't really know Haskell and what's going on with Haskell. And then you start to hear like, some of those other words I mentioned earlier, and you want to know more, but your day job, you don't always have time. So we got together and said, we're going to create a Haskell study group. And then I think right now we're about halfway through, but when we got to chapter 10, one of my friends in the Haskell study group told me that I was going to have fun with this chapter, and I groaned. I was just like, oh, really? Like, folds, right? Here we go again. Like, I don't, okay, what's so exciting about folds? And I'm sort of like, still at this point in my life as a developer, I'm still sort of stuck with that impression I had where I don't want to use a fold. I'm just going to use a tail recursive thing like I just showed you. So this I started working through the chapter, and this sort of made me start thinking about folds. And this chapter actually ended up being very instructive. So before we talk about folds in Haskell, first, I want to talk a little bit about lists. So in Scala, you can't really do, with the kinds of lists like that are in the basic collections framework, you can't do what you see here. You get an out of memory error if you try to build a big list. So here I'm trying to build a list that goes from 1 to int max value. And the range part, where you have in parentheses the 1 to int max value, that's a range, and that's lazy. But when you call toList, it tries to compute all the elements of the list, and you get an out of memory error. Okay, so that isn't very, very interesting, but this laziness thing is very interesting. So in Haskell, your lists are by default lazy. So the definition of a list in Haskell is here. There are two cases. So the first case is an empty list, or you have an element that's cons with another list, right? So I like to think of this as you know, the idea that you don't necessarily have to evaluate what that tail is on this list, or even like what the list itself is. So you have a cons with something, and the something doesn't have to be evaluated, and that's kind of the key. It enables us to do things like you see below. First there's a finite list, which is similar, but I mean semantically slightly different, where you have 10,000 elements in a list, but then you have an infinite list here in Haskell, and that's perfectly fine. Now we couldn't do that in Scala with the basic Scala collections. I use this Star Trek image over here because I think about the list, the tail of the list is not really materialized yet necessarily, right? So it makes me think of that, and that's a useful image for me. I guess it ties programming to watching Star Trek when I was a kid, which was a lot of fun. So in Scala, we have this thing called LazyList. And so what I've done here is I've declared a LazyList as a LazyList from 1. And you see in the REPL, you get this like not computed like message. That's kind of interesting. But that is the reason why you see that is because it hasn't actually evaluated every element of the list. And you can now use this list. It's a typed thing. You can use it. It's got to type it. And just like everything in Scala, you can pass it around. And it's super useful. So the expression evaluates, so you don't end up with this out of memory error. Now let's look at some folds in Haskell. Very similar to what we saw in Scala. So here we're folding over a list and we're doing an addition. Very similar. You have foldl and foldr. You don't have a basic just fold. Like, I mean, in Scala, you saw that fold is implemented in terms of findLeft. So it's really just reducing to the same thing. So here we have the two basic variations of foldl and foldr, and that's what happens. You get a result. So that's okay. That's interesting. How does the evaluation work? So that's something that I think if you're studying folds, you probably want to take some time and really like look at the definition of fold and at the fold functions and see how how expressions are evaluated. So what you have here is essentially like this just applies the definition of foldl. So at step 1, you have this call to foldl with a function, a 0, I should say an accumulator value of 0, and a list. And then at each step of the evaluation, the definition of foldl is applied. And so you end up at step 4, you have this thing, it's called a thunk. You have this thing that is evaluated this far. And now we don't need to call foldl anymore because we match the case where the list is empty, the first case in the definition. And so then we start doing the work to do the addition, right? So you have 0 plus 1. And then so at line 6, that reduces to 1. And then it just keeps going and then you get a result. Okay. So that is interesting. And then foldr is likewise interesting, but it looks a little different because of the way it's defined. So same idea, you're taking a foldr call and you're applying the definition of foldr. You see how foldr kind of keeps getting pushed out, like as it does the evaluation. And in the end, you get the same result. Okay, so that's foldr and how foldr works. Now I'm going to do, in here, there's an implementation of our find using Haskell folds. So this is foldr. So this is just basically, what I've done is I've zipped the elements of the list with their indexes and I defined a type so it would look different in the code. They're both, one's an int and one's an integer. That doesn't matter so much. But what this findRight thing does is, well, it calls foldr and it uses this check function. And the check function is basically looking at an element of tuple, which is an element of the list. And it says, well, if the n is the element at that list is equal to the thing we're looking for, then we return just I. That's equivalent in Haskell. That's the equivalent of a sum I. So this maybe thing is like an option in Scala, and just I is a sum, and then nothing in Haskell is a none in Scala. So it's very similar to what we're used to. So what this findRight does is it returns a 6. So you're looking for 7. These aren't shuffled here. You're looking for a 7 and you're zipping with the index and then you're finding the index where it is. So you get a 6 here. When you try to look for something that, and again, these are finite lists. When you try to look for something that isn't in your list, you get nothing, can't find it. And when you call findRight with infinite lists, and this is kind of the power of what you can do in Haskell, when you call findRight, you return just 6, but you have these infinite lists. So that's very interesting. It's different than the way things work in basic Scala. So Scala folding. So here is a find with findLeft. Now this isn't quite so good. Same idea. We have a findLeft function. It's got a check function. The order of the parameters is slightly different because of the way foldlefts work. But you see that when you call findLeft, you get your answer on a finite list. If you call findLeft on the finite list with something that is not in the list, well, you get a nothing. That's what you would expect. But when you start to work with infinite lists, you start to run into problems. So with findLeft here, what you end up with is a stack overflow. Now, 7 is pretty early in the list, right? But we're still stack overflowing. Can we even find 1? No, we can't, right? You can't even find 1, even though it's right there at the beginning of the list. You end up with a stack overflow. So this is rather interesting when studying Haskell and thinking about these concepts. So let's look again at the evaluation, but this here is the findLeft. So what I've done here, starting in the middle of the slide, at the top of the slide, I just have the definitions of the function, so you can see if you were to go through in detail how the evaluation proceeds, right? So you can see it's just calling foldl, and at each step, it's pulling something off the list, and it's never actually calling check. It's just building up this huge thunk, and because this is this infinite list, it just goes on forever, and it doesn't work. It crashes. Now with foldr though, with findRight, it's very different. You can see here that what's happening is we're actually calling the check function we're oscillating between calling check and calling foldr, right? So we're deconstructing the list, but every time we deconstruct the list, we check and we get to the answer. We get in this case, I did 3 because I wanted to fit it on the slide. It's not 7, but it's 3, but we get just 2. So this is sort of how the evaluation proceeds with findRight. And that's pretty neat. So we're going to get into this idea of strict and non-strict. So what does it mean? So non-strict semantics means that basically expressions can have a value, even if some of their sub-expressions do not. Well, let's unpack that. I'll give you an example. So if you have a function that takes 2 arguments, it's non-strict if it may not need to evaluate both of its arguments in order to return a result. So Haskell is one of the few modern languages that has non-strict semantics by default. So there's a lot of power in that. Nearly every other language, like Java, like many of us come from, like I came out of Java, has strict semantics. Now, of course, Java has some stuff now, and it may have the option to use call by name. I'm not sure. I don't look at Java on a regular basis, but basically every other language has strict semantics. And if any sub-expression fails to have a value, then the whole expression is going to fail. So with strict semantics, did I mess up this slide? I think I messed up this slide. With non-strict semantics, we may not need to evaluate a sub-expression. But with strict semantics, like we actually have to. So I may have to fix that slide, sorry. This non-strictness, though, is what allows programs to work with conceptually infinite data structures. Okay, so let's look at the summation again. In Haskell, you have this plus. In Scala, you have this plus, and you're adding 2 things together. Both arguments of the function must be evaluated in order to add, okay? That's why you can't take a sum over an infinite list with a fold, because like you just keep going forever. Our check function in Haskell is not strict. So our check function, if you look at the implementation, it says, well, if the key is equal to the value at this element, then just return just I, else findRest. But it doesn't need to know what findRest evaluates to. So Haskell doesn't bother to evaluate it. And that's really cool. So what happens for me is I'm trying to be a better Scala developer. So can I do this in Scala? And the answer is yes. We don't use it much, or many of us don't use it much. I've actually been discouraged from using it in production code at my current job, which is sometimes interesting. But you know, you can do this call by name and you can get this lazy evaluation in Scala. So what I then said is I want to implement Haskell style folds in Scala. All right. So this just gives you the definition of a, it doesn't even give you the full definition. It just kind of shows you what the LazyList class is. It's an immutable linked list. We call it lazy because it computes its elements only when they're needed. We saw this a little while before. Here's a little bit more on LazyList. So LazyList starts from 0. In this case, I'm starting from 0 and it's printing out this not computed thing. If I call head though, I get a result, I get 0. If I call tail, I just get another one of these not computed things. If I call lazy ints again, what's interesting is it memoized the 0. So it stored that and you know, it doesn't go and recompute that. So that's kind of good to know, I think. It's not going to be that useful for our purposes, but I think it's good to know that about LazyList. So what I've done here is I've just then I'll call tail.head and you'll see that down below you get the LazyList 0, 1, and then you get that not computed thing. So 0 and 1 are memoized. So I think that's really neat. So here we have my definition of foldr. This is a Haskell foldr that I've defined in Scala. And using the LazyList and using call by name. Interestingly, it's important that the function that you use has a call by name parameter. So if you see the second argument to f is call by name, that's kind of key for foldr. So this is essentially a translation of the Haskell foldr definition. And the same thing here, we have a translation of the Haskell foldl definition. And this can actually be tail recursive, which is another topic that I'm not going to get too deep into, but yeah, you can make this tail recursive and that's cool. It's pretty efficient. All right, so here's our implementation of findRight in Scala. It's the same thing you just saw in Haskell. It's got that check function and it returns a result when it finds it, and it doesn't have to do any extra work. So this is super cool. Like you can use the same kind of fold as you get in Haskell. You can use it in Scala. And when you try the findLeft version, you get similar behavior. You run out of memory. So you can't do the findLeft just like we could in Haskell because it's doing this whole thing where it's building up this huge expression. Now, Cats has these things. I was instructed by a coworker that I should look at Cats, and he was right. I did not dig into this. So if you want to do this at your day job, I would suggest looking at Cats. I haven't tested these. I haven't looked at them in detail, but you can find it. Many of you are probably familiar with Cats, so I would go look at that. So let's quickly revisit foldl. This example is the one with 10 elements in the list, and I've done the evaluation here, kind of built it out. And you build out this huge chunk. There's only 10 things, but once you get to the empty list case, then you can start evaluating. And the question I ask myself is, well, wouldn't it be nice? We know, if you look at line 2, we know we have to do a 0 + 1. Wouldn't it be nice if we could do that addition like sort of sooner instead of like wait to the end of building out the whole thunk? And Haskell, of course, has support for this. It has this thing called foldl prime, and foldl prime makes use of this special primitive system function called seek. And it basically what it does is it takes two arguments, and you want to, if you're going to use this, you want your second argument to reference your first argument. It'll evaluate the first argument, and then it will return the second argument. So that's what seek is doing. So what I've done here is with the evaluation is I've kind of shown how seek is working. And what you can see is like at line 2, you have this Z thing. And before you actually like evaluate, it has this special evaluation where it says, oh, okay, well, Z prime is 0 plus 1. So I'm going to then substitute that that in for Z prime everywhere. And so now I have foldl prime, and then I continue deconstructing a list and doing this thing. And I end up like, it just keeps going. And I end up with, in this case, we're doing an addition. So we're going to end up, if this is a finite list, we're going to end up with an answer. Of course, if it's an infinite list, it will never end because we'll just have to keep deconstructing a list that never ends. So that won't help us with that, but it will help us with this. So can I implement foldl prime in Scala? And yes, I can. And in fact, it's kind of cool. I just take off the call by name parameters, and the signatures are almost exactly the same. And the implementation is almost exactly the same. And the behavior is the same. This is some example where I'm trying to do a sum of a list with foldr, and I get a stack overflow. Here I'm doing a sum of a list with foldl, and I'm getting a stack overflow. And if I use my foldl prime implementation, I get an answer. So you can get the same behavior in Scala. Now, I did something interesting. So what I did in my findLeft prime in this example here is I actually had some print statements because I wanted to know, just sort of like to illustrate. I kind of figured out, but I wanted to illustrate what it's doing. And if we look at like calling this thing, we get some output that looks like that. So it's walking through, and it's like when it finds it, it says, oh, I found the key at this element. When it doesn't find it, it just keeps going. Well, this is what keep going means, right? So it actually like ends up finding 7, but then it keeps walking through the rest of the list. So this is not really like what we want. This is sort of like that case of iteration when we'd really like to stop, but we didn't stop. So this illustrates like what foldl can do and what foldl prime can do, but what it actually does is not necessarily what you want. So we get to the conclusion here. What have we learned? Well, what I have learned is that I can get beautiful folds in Scala, and I would look at cats if I'm going to try to do this in production. foldr is often the right fold. It works great with non-strict functions on infinite lists. Foldl prime is useful for finite lists, and it's best for strict functions like sum. And foldl is rarely useful. I think one of the things that was really cool for me is the exercise of implementing these things really drove home call by name in Scala. There was this sort of lack of confidence that like what call by, I knew what it meant, but I didn't realize that. I thought that if you had a call by name parameter and you're passing it to another function, that it would actually evaluate that. And it doesn't if the function you're calling is also taking a call by name parameter of that type. So, or of something that uses that type. So that's really kind of powerful. And it was sort of like the light bulb going off for me. And so I've concluded that Haskell style folds are pretty awesome. And I think we should care, because I think this really illustrates how learning Haskell can deepen your understanding of Scala. I want to say thanks to a bunch of my friends who make up the study group with me. Marco, I'm not sure if you ended up joining. I know Ben and Paul are here, so thank you guys for challenging me to learn and for the feedback. If you saw a version of this talk before. My friend Franco, I'm not sure if he's here, but he saw this talk, an early version of it last week, and got me some feedback, and it was super useful and super helpful. So thanks, guys. That's what I've got.
Very nice.
Thank you, Eric.
You're welcome. Sorry about the bugs in the slide. I've been doing some late nights.
I think that's when you discover bugs in slides. It's when you're presenting.
Yes, yes, yes. So I just like find that the whole like learning a new language is super exciting. Like it just makes me kind of get down and dirty with the computer and like, what is it doing? Like, why is it doing this? Why, why should I care? And I really want to be able to, when I do my job, I want to be able to, be someone who's kind of a master at Scala, right? So I'm constantly trying to get better at that. Reed is saying, I tricked him into a Haskell talk. Well done. Well, that's because we almost tricked you into a .NET job at Rally when Reed joined Rally. But we got it back onto a Scala job quick. We talked to HR and fixed that. So anybody have any questions?
I have a question.
I have a question.
Go ahead.
Here, let me just jump in. I might have missed this part about your tail recursion. Like, why not just use tail recursion for like escaping early out of these iterations? And I understand the infinite sequence is probably a big part here, but what was the big win for fold?
I'm not sure I understand the question. Sorry.
Yeah, like why wouldn't I just write a tail recursive function instead of fold?
That's a good question. I recently, in my work, I actually did a tail recursive function because I was going fast and instead of a fold. But the other reason I did look at it again later, and I realized that I was actually deconstructing two lists, and it wasn't like sort of like parallel lists that I was deconstructing like the same, like the examples I showed you with finding things, I was finding the index. So I was trying to deconstruct two lists, and it doesn't occur naturally to me to use a fold for that because of the different conditions involved. It looks like Devin has something to say. I'll come back to Reed and see if I got you answered your question. I'm not sure if I have, but Devin, your hand is up.
Yeah, to at least give some sort of anecdotal evidence for why to use fold, and in particular why to use cat's foldable. One of the things that I got very early on in my Scala adventure, I listened to the Odersky and two other professors give that MOOC talk a long time ago. One of the things that I got out of that really stuck in just in the back of my head, and it wouldn't get out, was not re-implementing flow control. A lot of what exists, and this is almost a direct transliteration of what that professor said, but a lot of what exists in flow control libraries, CATS having a wide variety of flow control available in library form, is explicitly formalizing that which you have done just kind of bespoke before. You can implement a while loop, you can implement a for loop, you can implement do while, whatever. The challenge is figuring out the right fit for your problem and getting the advantage of well-tested structures, as well as communicating to your reader using this kind of shared library of terms, the exact semantics that you're trying to convey. So instead of someone sitting down and trying to read what you have, like maybe nested loops or something like that, it's possible, and this is what we used to do. But now the like in Scala, the idiom zip with index and then fold left, it's like, that is so much more terse, and I know exactly what's going on. So I found that really compelling, and then combining that with with some advanced cat stuff like the monad transformers and stuff like that, where you can actually start talking about defining your own structures that piggyback on these existing type classes. It quickly allows you to express a whole lot of functionality very quickly. So I'm a convert, certainly.
Yeah. As we're talking, and as I'm thinking about it, I'm realizing that that example in my current production code probably could be implemented with foldLeft. I'm not sure how readable it will be because of the complexity involved, but I may try it just to see if it's an improvement. I've got more hands up. I think, Paul, your hand was up first.
Yeah, I think I was just actually going to echo pretty much what Devin had to say. I think that with kind of cats, it's kind of analogous to structural typing. If you say, well, this thing has to be a functor and foldable, then you have these nicely tested, very terse kind of operations that you can use. I'll show you something. I'll share something later with you that I wrote that is 4 lines of exquisite beauty, going into containers and operating on them, since I know that they are foldable and functor. So that's it. Just cats is beautiful.
Yeah. Nathan, how about you? Looks like your hand's up.
Yeah, so my question was on the call by name
Yes.
values. Those are sort of semantically, well, sort of. No, okay, I take it back. They're similar to like a function from like unit to something, but they're obviously lazily evaluated and only evaluated once, but the function is not. Do you know under the hood how they compile or what performance differences you've got like between one or the other?
I do not know that. Devin, you may know that. Not to put you on the spot, but you strike me as the type who might know that.
I was actually answering a question in chat. I just heard, do you know how something is implemented under the hood?
Oh yeah, so Nathan was asking asking about the difference between like the call by name parameter that like, you know, you can declare one that takes like a unit, and you can declare one that like just produces a value, right? So you're not actually it's not a function that you're passing, it's just a call by name parameter. And I think Nathan, you expressed the question better than me actually, but I'm not sure how it's implemented under the hood, if it's any different.
Yeah, I always assumed that call by name was just a bespoke syntax for a unit function.
Yeah, and it may be.
Actually, I believe that's true.
I know the single evaluation is probably like the main sticking point, but I'm not sure what that would impact the bytecode, or how that would impact the bytecode.
Yeah. Going back to Reed, did we get you a satisfactory answer?
Yeah, I think so. I think my question is really around readability. And so like if it is this like shared lingo almost, like to boil it down, like everybody will understand in the community like what I'm trying to write, not just this one-off maybe well-named tail recursive function, but like I don't have to roll so much by hand if I'm just going to use the same idioms that the community's using. So yeah, I think you did.
Yeah, cool. Glad to hear it. Anything else?
I think one of the things obviously leveraged heavily was just like the non-strictness and stuff on the Haskell side, and you explored that with folds. Are there any other like avenues or areas in Scala you think to like bringing that to would bring it maybe similar or additional value?
Possibly. I think so. Like as I continue working through this book, learning Haskell, I think I'm going to be constantly trying to see how what they present like can be related to Scala. So I think as I continue to learn more about Haskell, I think I'll be able to answer that better. I don't know yet. So yeah, I think there's it's just there's so much there, and it's super exciting. I think if I had not gone down a career in having a career in software engineering, I would have got a PhD in computer science, and I probably would have studied programming languages because that's what I love. Like I just love thinking about it. So but I don't have the answer right now.
Totally fine.
And of course, I try to do this in between my day job, right? So
And we thank you for it. Appreciate it.
yeah, well, I hope it was useful for folks. I hope thinking about this is useful, and I'll try to fix up my slides, and I can get them to Andy, and he can post them. A couple spots I gotta fix, but
May take a little bit, but once I'll get the video posted and uploaded to our YouTube as well. At some point.
Cool.
Yeah. I guess if there are no other questions, well, thank you, everyone. And again, thanks again, Eric. Appreciate your time.
yeah, I'll have to think about what my next talk will be. Oh, Devin got his hand up again. Are you waving? Oh, you're clapping. Oh, that's what that is. All right, thanks everybody.
Yeah, thanks all. Appreciate it.
All right.